Kind of amazing that they have enough bad chips to actually make a whole run of laptops.
So what's interesting is Nvidia's B100 and their B200, they're almost the same specs. The only difference between the B100 and the B200 is the binning. Jensen's smart.
Intel having the ability to bin all their chips made them a little more lax on their process control. Welcome to Supply Chain. I'm John from Asianometry.
I'm Tim Culpin of Culpian.
Today, let's talk about the Macbook Neo.
Oh, the Neo. It's a hot item.
Very hot and running out too. So
it is running out, yes. The last I checked, it's about a 4-week wait to get one delivered.
Really?
Yeah.
They're selling them as fast as they can.
Yeah, they really are.
People thinking that people thought it was gonna sell well as soon as it came out, and then it's immediately selling well as soon as it came out.
But it's selling more than Apple had expected. And the issue there is they are limited in how many more they can make. They basically have their upper level of supply already capped last year or the year before when they made the iPhone.
And why is that?
Well, a lot of people were surprised to learn that the MacBook Neo is really just using a binned iPhone Pro chip. Right? Now, the iPhone Pro comes with various cores. Cores are the hottest item in chips these days. You have lots of different cores. But with binning, you test the chip, and sometimes you find that a part of the chip doesn't work. Instead of throwing it out, you just turn that part off. And so around somewhere between 20-30% of the iPhone chips didn't work perfectly. And that's normal. That's not considered bad yield. But Apple, being the masters of recyclers, said, well, we could make a product out of this. And so they took a lot of those, the ones that were still usable, turned off a core, and said, all right, we'll use it in another product. And that product is the MacBook Neo. And what's interesting is it's basically a free chip. Right? They don't really have to pay for it because it didn't meet spec. So it's not counted in their cost accounting. And so they have had a lot of these chips sitting around in warehouses, probably in Tainan, where TSMC has a fab, and not being used until Apple was ready to put them into a product.
It's kind of amazing that they have enough bad chips to actually make a whole run of laptops with it.
Well, remember that for every product, iPhone product, they sell in the order of 150 million units. Not necessarily that year, because they might sell the next year and the year after. And it's a very long tail. Most units of an iPhone of that year's model will be sold, in that 12 months. But then you get more a year or so after. And so if you think of 150 million units, and if you then think, well, 10% is binned, which is 15 million, now we're talking about a MacBook Neo run. So it's not bad, right?
Well, the interesting thing is that binning, though Apple seems to be the master of it now, binning is something that's been done for decades.
Yeah, I was doing research on this.
Oh, really?
One theory, which I don't think is quite correct, but it was a theory that came up in my research, was that one of the early inventors of binning was Morris Chang. Because he really understood the importance of yield. But the first example of binning I could come across was from Intel. They had the EEPROM, which was basically a programmable memory. We tend to think of NAND as being the storage type of memory, but back then it was EEPROM. And they had a 16 kilobyte version, but they did have batches or many amounts of them where parts of the chip didn't work, so they just sold it as an 8K EEPROM. And they didn't have to throw them out. They just said, all right, it's not a full 16K, it's only 8K, but it does the job. And so they would turn off the chip, and you can do that in various ways. You can, I think the way they did it was the wire that they had coming out of the chip, they just kind of snipped it and grounded it. They didn't actually plug it into the motherboard. But there's other ways you can do it through firmware or whatever else. But yes, that was in the, I believe, the 70s or 80s, so 40 years ago, 50 years ago, one of the earliest examples of binning. And it's been fundamental to the chip business since then.
I remember one of the examples that I did for a video that I was doing. They were making radios,
Yes.
like a transistor radio, and the actual transistors radio. And then they had transistors in them. And what they would do is that all the transistors came out in terrible quality or varying quality. And what they would do is match them up. They would take two various transistors of a certain quality, like a certain output strength, and basically pair them together. And that was in a way to kind of, get the quality of the amplification, the radio, to get the radio working the way it was. That kind of sounds like binning.
It is kind of binning. When the transistor matching that they were doing back then is, well, the way I would define binning is this. If the underlying production process is the same, and so the physical die or the product is the same, but the specs that it can run at or is operated at is different, I would call that binning. So with these transistors you talk about, they were basically made through the same factories, the same process, but just some came out not as good.
Right.
And couldn't be run at the same level. And this is essentially what is binning. It's not a different chip. It doesn't go through a different production process. It's the same lithography, the same masks, and the same process. But at the end of the whole process and after packaging, you just can't run it at the same level as the premium chip or the best chip with the best yield. That's basically what binning is.
There's a lot of, when I'm digging into the literature, there's a lot of research done into the sort part of it, the binning part, the sort algorithms, the various parts of, like, how do you determine how do you rank it, basically, kind of stack rank them all and then kind of sort them out. So that's kind of an underrated part of kind of the binning process.
Yeah, and a big part of it was thermal. So in the 90s and the 2000s, essentially one of the major areas where you're kind of good, bad, or upscale or low scale, or high bin, low bin, was how quickly you could run it, like what clock speed you could run it.
Speed binning. Yep.
Yeah, before you got to a thermal level that was not acceptable. Either it was too hot for the system, or the chip itself was going to fail or melt down, or you get short circuits or whatever. And so you do thermal testing, and then you work out how far you could push it. And we saw that, Intel, AMD, those guys were doing it in the 90s and 2000s. And so Celerons and Pentiums, right, 25, 30 years ago, were all, for a certain period of time, for that batch of, that 6-month period when Intel or AMD was putting them out, would do the binning. They would test it and say, all right, we can run this at 666 megahertz, but we can only run this one at, say, 566 or whatever. And they would just label it as a different chip. It would be the Celeron this or the Celeron that, and you would just have different labels. But if you looked at the spec sheet, everything else was kind of the same die size, same amount of pins, the same socket, all that kind of stuff was just like, this one is run at this speed, this one's run at that speed. And you could enforce it through firmware, right? You could just force people not to do it. But then if overclockers wanted to, they could push it, right? They could get that chip and push it above its rated speed. But it meant that Intel and AMD weren't throwing out chips. They would just say, all right, so they'd go to the brand names and say, all right, well, you want a cheaper chip? Well, the premium chip is costing $100, but this down bin one, $70. We'll give it to you for 70 or 50. And, the decision on what price was very much a marketing decision as much as anything else, because otherwise it'd have to be thrown away. But binning became such a part of the industry that chip makers knew, kind of within a few percentage points, when we do this run of this chip with this design, with this lithography process, we're probably going to get 30% will be not run at the highest spec. We'll have to downbin it, and within that 30%, maybe 20% of those would be the medium bin, and another one would be the lower bin, and others would be just scrapped. They couldn't run anything at all on it. And they would kind of have an idea 6 months ahead before they're even coming off the production line what they could expect, because they'd been doing the testing through the process of making the chip at the various stages of testing, and also in the packaging and testing process. And then we'd kind of have a pretty good idea of what they'd be likely getting out of the end of it. So it's part of the business model now.
To argue that Intel having the ability to bin all their chips made them a little more lax on their process control?
There is...
So like TSMC doesn't earn money from binning, does it?
No, but Apple can. So Apple can make the decision, and Apple does make the decision when they're making, say, an iPhone chip. All right, if we add 5 more steps of testing at various stages of the process, we can make sure the yield is better because we know there's a problem and we tweak it, or we just accept it. And we know that at the end of the process, once it's packaged, it's just going to be a downbin chip or a higher percentage of downbin chips. So you have to make this decision. Do we want to slow down the production line, tweak the tooling on the production line, or tweak the parameters on the production line to get that yield higher, but that slows the output through? Or do we want to just kind of not bother with that, except that we're going to have a lower yield of the premium, perfect chips and a higher proportion of downbin chips? And then you can run the numbers on it. Well, what percentage? How many wafers are we putting through? How many chips are we getting per wafer? What would we use it for later? And that really is the Apple kind of production business model right now. They know that a certain percentage of the wafers that go through will have a certain percentage of chips that will be premium, that would go into the highest, MacBook Pro or whatever, and others would be not quite good enough and would go into an iMac. Or some would go into the premium Pro Max phone, and some would go into the Air, or the Apple TV, or the HomePod. See, a lot of people are not aware of this. The HomePod and the Apple TV use downbin chips, right? So the Mac Neo is not the first product using downbin chips. It's been part of Apple's thinking for a very long time.
Does it mean that my HomePod can run 4K video editing?
Theoretically, it could, unless that was the part of the chip.
Tiny little screen.
Well, there's a concept in computer science and electrical engineering that every computer can all do the same thing. It's just some can do it quicker, right? They'll always come out with the end result, but some will get there more slowly, and some will get there quicker. So yeah, in fact, if someone really wanted to pull apart the MacBook Neo, pull out the chip and then shove it into their own homemade iPhone, they could do it. It's theoretically possible, but where the limitations might be could be on the firmware and other areas where software controlled, or maybe they've done something where literally on the die they just get a probe and deliberately short circuit a certain area, so you absolutely cannot use it. Those things are possible. But, the recipe for making that chip is pretty much the same. It's just some didn't come out quite as well as the others.
How do you think the success of the MacBook Neo, because they made this on last year's iPhone volumes, now they're supposedly you're going to say that you reported that the idea for the Neo 2, whatever that is going to be based on the iPhone 17 run. Do you think, though, the success of the first run of the Neos changes that calculus?
Well, the first thing to remember about the current iPhone is that it's doing better, and therefore more of the chips are being made and put through TSMC. So on that basis alone, and let's assume the yield and the bin split between the premium and the down bin is percentage-wise the same, you are naturally going to have more down bin iPhone chips that can go into the next Neo. And that could be, a scale of 50 to 80% more chips available, which means they can make 50 to 80% more MacBook Neo 2s. That's the first thing. The second thing is, as we know, capacity is very tight at TSMC, and everybody's struggling for capacity. What Apple could do is they could say to TSMC, look, don't worry about slowing down the line and just kind of tweaking it to get the better yields out. Let's just push it through. We won't do as many tests as we might otherwise do. Let's not worry so much about the yield per se, or at least the yield within the binning tiers. And we win either way because we can push more wafers through per day or per month because we don't have to slow down the line to do the testing and the tweaking. And yes, we get maybe a higher amount of down bins than we'd otherwise like. But on a net basis, because we're not slowing it down, we're going to get more of the premium chips and also more of the down bin chips. And so that's okay. And that's the way semiconductor manufacturing works. If you want 100% yields, you can do it. But you're going to sacrifice scale, right? You're going to sacrifice throughput. And right now, nobody in the chip industry wants to sacrifice throughput because capacity is tight at the leading edge. In AI and everything else, everybody wants throughput as much as they can. And so what I'm hearing is that more and more clients are willing to sacrifice yield to an extent to get that extra few, 1,000 wafers a month out of the production process.
Interesting. And then one of the things, a lot of YouTubers, bad YouTubers, picked up your report.
Yeah.
And a lot of them, there was one thing that circled around that's like, oh, the DRAM is going to go up. Can you fix that?
Well, that may or may not be true. I think one thing to remember is, unlike AI chips where the DRAM, which we call HBM, right, high bandwidth memory, is like literally fused into the same chip through the CoWoS process. With iPhone chips, yes, they have DRAM, but it's kind of just welded on top, right? I mean, it's kind of
info packaging, yeah.
Yeah, so you can fabricate the whole CPU, GPU thing that they have, the system on chip, which then goes in a package. And then later on, you can decide how much DRAM you're going to put on it. Now, I wrote a piece a few months ago that Apple was ready to scrap a whole lot of chips for the iPhone Air. And one of the reasons was they, as far as I understand it, my sources here in Taiwan were telling me they'd already fused the DRAM on. And they couldn't unfuse it, right? Which was unfortunate because their suppliers would have loved being able to get their hands on that DRAM, right? So if you're a Foxconn or a Quanta or a Pegatron or anybody in the supply chain and you could get your hands on those chips and say, we'll take that DRAM, you'd have been very happy. It wasn't possible, it wasn't practical really to go back and like unstick all these DRAMs that were already fused to the CPU. But if Apple is finding out, if they're doing the binning process between the upper and lower tiers of the bin early on before they've put on the DRAM, which I believe they do, then they can still make the decision of how much DRAM they want to put on the Neo 2, even though the actual CPU itself is somewhat fixed. So the DRAM decision, just because the phone has, I think, 16 gig of DRAM or 8 or whatever, doesn't mean that the MacBook Neo 2 will have that same amount of DRAM. But the flip side is DRAM is such a premium now that if you go from, say, 8 to 16 or 4 to 8 or whatever, well, you're doubling the price of DRAM. And a few years ago, the amount of DRAM, like the cost of a DRAM per phone was relatively small. The percentage of bill of materials was like low single-digit percentages. But now it's like into the double digits and higher. So really, do you want to stick a whole lot of really premium DRAM onto a laptop that you're selling for $500? Well, that's the decision Tim Cook's going to have to make, right? I don't think I want to do that. I want that. A, can I get my hands on the DRAM? And then I've got to pay for it. So if I can, first of all, get my hands on the DRAM, I might want to use it for something else. And B, I probably don't want to allocate that much cost of bill of materials to a low-priced laptop. Because one of the great things about the Neo 2, the Neo in general, is because you can kind of look at, and Ben Thompson wrote this, it's free chips, right? They look at it as free chips. That makes the margins on the Neo fantastic. But when you're paying a whole lot more for DRAM, those margins start to get, really shrunk quick. So there's not a lot of room for Apple to play with the margins when DRAM prices are going up.
One of the interesting things is that kind of like this bidding things happens to everyone, right?
Yeah.
You have these companies. If you're making chips, I wonder what Qualcomm does with their bidding. But you mentioned another company. There's another company out there using 3 nanometer.
Nvidia.
So
what's interesting is, I hadn't realized this, but I asked around and found out, and here's what's interesting. If you go online and pull up the spec sheet for Nvidia's B100 and their B200, they're almost the same specs. Now, the amount of flops you can get out of, or teraflops, right? Flops being the amount of floating point operations per second or whatever. You get more out of, one of them than the other. But that's because they've been essentially binned, because we talked about thermal design power or maximum thermal design power. If you speed up the chip, the actual clock speed, you're getting more heat dissipation, and that's a problem. So it's my understanding that the only difference between the B100 and the B200 is the binning. You're running the B200 at 1,000 watts, or theoretical maximum of 1,000 watts. But because the B100 didn't come out of the oven quite as nicely as the B200, they can't run it as fast or as hot. So they run it at, up to 700 watts. And therefore, you're not going to get the same teraflops out of it and the other performance. But it's my understanding it's exactly the same chip, the same lithography process, the same masks, everything's the same, all the way to the CoWoS, I believe. You look at the spec sheet, it's the same HBM, same amount of HBM, all of that, the throughput speeds, all that the same. It's only just kind of like what you can squeeze out of it. It's the same chip, it's just been binned, which I think is fascinating because this is a really expensive series of chips. But Jensen's smart, right? He's not an idiot. Why would I throw out those chips, right? I can just relabel them because Jensen and Nvidia have been doing binning for years, well before the AI era. But the GPUs that he's been churning out for the last 20, 30 years have always been binned. It's always been a part of what Nvidia does. And every chip maker would be stupid not to do binning.
Well, today we talked about binning. You've been listening to Supply Chain. This is John from Asianometry.
I'm Tim Colpin of Colpium. Thanks for joining us.